Hi, so welcome to lecture 2 for our classical physics course. This video will talk about kinematics, and this is part 1 of the video. This will cover basic theory of kinematics, and then part 2, which will be the follow-up video to this, we'll be doing some advanced problems. So part 2 video will cover some advanced questions that will better explain the concepts in kinematics. So let's start. I want to make a few points before we begin our discussion of physics. So first thing is we have to understand what a frame of reference is. Frame of reference. So frame of reference is basically your point of view, right? So every time in physics, there will be quantities that will depend on where you are and how you are seeing things, right? So if you think about velocity, for example, or even acceleration, right? All of these things are frame dependent. So if you are traveling in a car and you see another cycle going by, then you can definitely notice his velocity to be something, but you are observing from the car's frame of reference. And in case someone was standing on the ground next to the bicycle, he sees a different velocity. So all of these quantities are turning out to be frame dependent quantities. So always keep in mind that this frame of reference means what is the observer's point of view and who is the observer. So before solving any question, you need to specify who the observer is and what he sees as the values of these quantities. Obviously, some quantities are not frame dependent, some quantities are frame dependent. So as we go further in our study of physics, we'll realize which is which, right? The second thing that I want to talk about is coordinate systems. Coordinate systems. So what are coordinate systems? Now, basically, suppose you are this observer and you see something traveling with some speed, right? Now, this already is your frame of reference. You have already defined your frame of reference. This is the observer. It is his frame, right? However, you will not be able to meaningfully assign direction and magnitude to this velocity until you define where is your x-axis, where is your y-axis, and where is your z-axis, right? So unless you say that this is my xyz, or you can place your coordinate axis here, let's say x, y, and z, in that case, then you will be able to say that the velocity is equal to something v in the I cap direction, right? So if you choose your x-axis, y-axis, and z-axis to be something like this, and this is a second coordinate frame, then your velocity will be different because you will be expressing your velocity vector in terms of this coordinate axis, right? So it is not just enough to talk about frame of reference, you also have to put a coordinate system in that frame of reference. So that is something that you should be aware of, because all of these choices determine how you solve problems. And that is what this course is going to be about, where we are learning all of these concepts to be able to solve real world problems, right? So let's go ahead. The next thing that I want to talk about is time. So now everyone knows what time is, but in a physical sense, what do we mean by time? So the time of an event in a physical sense is basically simply the reading on the observer's clock. The reading on the observer's clock, right? Now, what we can say is that in classical mechanics, time is an invariant. In classical mechanics, time is an invariant. What do we mean by an invariant? Invariant in the sense that if you have two observers A and B, two observers A and B have synchronized their clocks, right? If they have synchronized their clocks, that both of them started their clock at say 10 p.m., right? And their clocks are showing the same reading, right? Then after that, let's say A does all sorts of things. He goes around with having some velocity, some acceleration in some arbitrary direction. B was doing other things. He was going around a circle, or he was traveling with a constant speed, or he could do any sort of motion, going around a circle, traveling with constant speed, whatever, right? At the end of that experiment, A and B will still have the same time on their clocks, will still have the same time on their clocks. So basically what that means is all of these activities, all of these different types of motions and accelerations do not affect the time on the clock, right? Once they were matching in the beginning, they will forever be matching. And that is our understanding in classical mechanics. Obviously, this is not the complete truth. So if you go to the realm of relativistic mechanics, you will realize that your motion or your acceleration, all of that influences the way your clock runs. So in relativity, time becomes a factor that changes according to your behavior of the system, right? But we are not going to concern ourselves with relativistic mechanics right now. We'll think of time as an invariant for the purposes of our discussion in classical physics, right? Now, with these background terminologies sorted, let's get to the kinematics part. So kinematics, basically we talk about certain quantities. The first quantity that we'll talk about is displacement. I will quickly define all of these terms and then we'll get to some applications, right? So displacement S vector is the change in the particle's position vector. Change in the particle's position vector from an initial position vector, from an initial to a final state. Position vector is R from an initial to a final state. To a final state. So what this means is S vector is simply equal to R2 vector minus R1 vector, where how do you define this position vector? Position vector is a vector drawn from the origin of coordinates to its current position. So let's say a particle was here. This is your position vector initial. And let's say after some time it went to this point B. This is your position vector final. So now displacement vector is basically R2 minus R1, which is basically this particular line. This is your R2 minus R1 vector. That is defined to be your displacement vector. Now, displacement is obviously different from distance. Displacement is different from distance, in the sense that distance is the actual path traveled, right? The length of the total path traveled. If suppose, for example, particle A moved from A to B and then came back B to A, you would say that displacement is 0, but the distance was double of this length, right? So I'm sure all of you are familiar with this distinction, so I'll not dwell on it too much. Let's go to the next concept, which is the concept of velocity. Velocity is defined as the rate of change of displacement. Rate of change of displacement. So we define it anytime we have a rate of change of something, there basically we are defining it as a derivative. So it can also be written as the rate of change of position vector of a particle. Rate of change of position vector of a particle. Why is it being written as rate of change of two different things? So let's see why. Because position vector of a particle is not the same as the displacement vector, right? So what do we mean by this two different definitions that I have given you just now? So we have defined S as what? S was R minus R naught, where R naught is the constant initial position vector, and R is the current position vector, Now, the current position vector obviously is changing because the particle is moving. So this is basically a variable, whereas initial position is whatever it was in the beginning. So this is actually a constant. So if we define velocity as rate of change of displacement vector, it is basically going to be d by dt of r minus r naught, where derivative becomes dr by dt minus 0, because This was initial position, and initial position doesn't change with time, right? So dr by dt of that will be 0. So therefore, velocity can be defined in two ways. Either you define it as a rate of change of displacement or rate of change of the position vector of the particle. So these are both equivalent and identical definitions. From here, we get the condition that ds is equal to v into dt. And if you integrate this equation, integral ds becomes integral v dt. And basically that means from some time, from initial time to final point, you can take the integral and you'll get the relation s is equal to integral v dt. Basically, total displacement can be calculated by integrating the velocity function with respect to time, right? Now, what about speed? We have defined our velocity function properly, but what is speed? So speed basically refers to the magnitude of the velocity vector, not the direction. Magnitude, but not direction of the velocity vector. So I'm sure you've seen this before, but what I will explain here is quite important, and you should pay attention to this part. If your velocity vector is dr by dt, notice that I have drawn an arrow over the r vector because this is rate of change of position vector. R vector is position vector of a particle, of a moving particle. So how fast does the position vector change? That gives you a velocity vector. Now, if I want to find speed, speed will be equal to mod of v, right? Speed is equal to mod of v. So you can think of it as rate of change of distance, right? Rate of change of distance. And distance basically differs from displacement in the following way. So if displacement was defined as a tiny displacement was defined as your dr vector, a tiny distance covered, the tiny distance covered here would be mod of dr, right? Because if your displacement was negative, distance is still positive. So therefore, you just have to put an absolute value sign on the displacement to get the distance vector. So if rate of change of distance is being asked, then you just have to do mod of dr by dt, right? Because mod has to be there because mod was the tiny distance, right? So mod dr by dt basically. This is just like saying mod dr by dt, which is the same as mod of dr by dt. So your speed v, which is written without the vector sign, is equal to mod dr by dt, and your velocity was equal to dr by dt, and all of this is definitely different from dr by dt. Now, what is this dr by dt? R here is the magnitude of the position vector, right? This is not equal to speed. So I will explain this with an example. People get confused between this term and this term. Okay. So there is a difference between when I say dr by dt and mod of dr by dt. This term is speed. This term is nothing related to speed. So let's discuss this with a particular example. The example is this. A particle moves along xy plane at a constant velocity of 10 meter per second in the positive x direction, okay. When the particle is at 3,4, find first dr by dt, which is basically velocity, then find speed, and then find dr by dt. And this is nothing related to speed or velocity. So let's understand what is going on here. So what I will do is I will draw the position of the particle here as 3, 4, and this is my r vector at this moment. And we know that the particle is going forward with the x direction, right? Particle is going forward with a velocity of 10 meter per second in the x direction. So since that is already given, your velocity vector can be written as 10 meter per second in the I cap direction, right? So that is equal to my dr by dt. So first part is very obvious. It is 10I, right? Second part is also obvious because second part is just mod of speed is just mod of velocity vector. So the answer for speed is just 10 meter per second. It doesn't have a direction. But what about this third part? What is this dr by dt? So let's think about what happens if you remove the, this is your r vector. If you remove the vector sign from the r vector, you get the length of the r vector, which is basically, this was r vector, and r is just simply this distance, right? So this distance r at an arbitrary point would be root x square plus y square at point x comma y, right? By Pythagoras theorem, if you are at a point x comma y, r will be root x square plus y square. So if you do r square, you'll get x square plus y square, correct? And if you do differentiation here, you'll get 2r dr by dt is equal to 2x dx by dt plus 2y dy by dt. So what you get is 2r dr by dt is equal to 2 times the x coordinate. Right now, let's put the values now. Right now, your x coordinate is 2 into 3, and your x velocity is 10, right? Dx by dt is your velocity in x direction. So 2 into 3 into 10 plus 2 into y coordinate is 4, and velocity in y direction is dy by dt, which is 0. So you get basically here 2r dr by dt is equal to 60, right? 2r dr by dt is equal to 60. So that means dr by dt is equal to 30 by r. And what is my r at this moment? R at this moment is by Pythagoras theorem just 5, right? So dr by dt is coming as 30 by 5 or 6, right? So this dr by dt is the rate at which the distance from the center is changing, right? Distance of this point from the origin, that distance is changing at the rate of 6. And that has nothing to do with the speed of the particle, right? So you should understand clearly that this is completely different. This is 6, this is 10, and this is 10 meter per second I cap, right? This is 10 meter per second, and this is 6 meter per second. But this doesn't have a direction, and this is not related to speed here, right? I hope that example explains to you the difference between these terms, and do not get confused by these. So after that, let's look at acceleration. You probably already know this, so I'll not spend too much time on this. Acceleration is defined as dv by dt, and you can find out the first law of motion, first equation of motion by doing a dt integral from 0 to t will be equal to the integral of dv from u to v. Basically, I'm writing a dt is equal to dv and then integrating from initial time to final time t and initial velocity u to final velocity v. And this equation, basically, if this becomes left, RHS becomes v vector minus u vector is equal to integral of 0 to t a dt, right? And if you basically assume that acceleration a is constant, then the a acceleration can come out of the integral, and you will get a integral dt from 0 to t is equal to v minus u, and you get basically v is equal to u plus at. This is your first equation of motion. And using that equation, if you write vs as ds by dt is equal to u plus at, using that equation, integrating this, what you will get is integral of ds from 0 to s will be equal to integral from 0 to t u plus at dt. And what you get after the integral is basically ut plus half at square is equal to s. So that is your second equation. The third equation of motion, this is the second equation of motion, this is the first equation of motion. The third equation of motion will come if you express your acceleration, which is the rate of change of velocity, in this way. You write it as dv by ds multiplied by ds by dt, which becomes basically dv by ds multiplied by v. So you can write it as a ds is equal to in v dv, right? And integrating this again from initial u to final v, and here 0 to s, initial 0 displacement to final displacement s, and assuming that a is constant, you can write a outside the integral, and it becomes a into s is equal to v square by 2 minus u square by 2, and therefore your equation becomes finally, this becomes v square minus u square is equal to 2a dot s, and you can write v square is equal to u square plus 2a dot s. So that is your third equation of motion, right? So these three equations of motion are obviously only valid when acceleration is constant. You have to remember that acceleration has to be constant for applying these three equations of motion. So now what we want to do is discuss a special case of kinematics, which is called the projectile motion case. Now this is available in all standard books, so I'll not spend too much time thinking about the basic derivations. I'll quickly show you what happens here. The key point that I want to stress on a lot here is that motion along two perpendicular directions is always independent of each other. Directions is always independent of each other. So what do I mean by that statement? Independent of each other. I want to explain this particular statement here. So what I want to say is, if there is a projectile being launched, right, with some initial velocity u and at an angle theta, I can always put a coordinate frame like this y and like this x, right? What I want to suggest here is that the motion in the y direction, depends on your vy and your acceleration in the y direction. And this motion is completely independent of the motion in the x direction, which depends on your vx and the ax, right? So x motion can be calculated separately and y motion can be calculated separately. Y motion can be thought about separately. Y motion is separate. So these two do not affect each other. That is what I mean when I say that they are independent of each other. So this understanding quickly gives us all of the results of projectile motion. So if you launch something with u at an angle of theta, let's call it actually v for the time being, v at an angle of theta, then we first find the time of flight. Time of flight you find by thinking about how long it remains up in the air, right? So it will remain up in the air because of its y motion. It will go up and it will come down because of its y motion. So what is the component of its velocity here? It is v sine theta up and v cos theta this side. And another point to remember here is that while it is flying, the body is always accelerated down by gravity by g. But this acceleration is vertically downward, so it is completely in the y direction. Completely in the y direction. There is no component of this acceleration in the x direction, right? So analyzing the y coordinate motion, you think about it, that the vertical velocity was v sine theta and the acceleration was minus g. And therefore, these two things determine how long the body stays up in air, right? So the time taken to reach highest point, would be basically v sine theta by g, because you will apply the equation of motion v is equal to u plus at. So final velocity at the highest point has to be 0. Then only it will stop there and come back down, right? So Final velocity is 0, initial velocity is v sine theta, deceleration is minus g, it is in the downward direction. So the time becomes v sine theta by g. Now, if it takes this much time for the velocity to go from v to 0 here, it will take equal amount of time for the body to come back the same distance, because velocity goes from 0 to v when it comes back, right? You can confirm it by applying the equations of motion yourself. You will get total time of flight will be double of the time taken to reach the highest point. Total time of flight becomes basically 2v sine theta by g. So basically this concludes our understanding of the y direction motion. You can also find the height it goes up. The highest point will be basically s is equal to h is equal to ut. So v sine theta into t. T is v sine theta by g minus half into g into t square. So v square sine square theta by g square. And this total height becomes v square sine square theta by 2g. So this height comes, the time of flight has come. Once we have these two things, the range of the projectile can be quickly calculated, because range is the distance in the x direction that the projectile goes before it comes back down. So that will depend on the x motion, and x direction there is no acceleration, and therefore there is a constant velocity of v cos theta in the x direction. So we are calculating now x motion separately from the y motion, and we are saying that the range will simply be v cos theta into total time of flight, which is 2v sine theta by g. Okay, so this becomes your equation, v square sine 2 theta by g, and we get the regular formula that we have for range. Now range is obviously maximized when sine 2 theta is equal to 1, basically theta is equal to 45 degrees. So these are standard results that you probably are already aware of. Let's talk about the equation of the trajectory of the particle. Equation of the trajectory of a projectile. Okay, so trajectory of a projectile, what do you mean by a trajectory? A trajectory basically is an equation of the path. Trajectory means path, and basically it is connecting the x and y coordinates of the particle, connecting x and y coordinates of the particle. So how can we do that? How can we find that equation which connects x and y? So it is quite simple actually, because we know that y coordinate motion is independent, x coordinate motion is independent. Let's say it was launched with v at an angle theta, right? So your x coordinate motion is very straightforward, because v cos theta is the speed and there is no acceleration in the x direction. So your x position will simply be v cos theta into time, right? Your y position will also come by a simple second equation of motion that we had. We will say y is equal to v sine theta ut plus half at square. So v sine theta into t, and a is minus g, so minus half gt square. So this is your y motion, this is your x motion, and now I want to connect y and x variables with each other. So how do I do that? I do that by eliminating the t variable. So t basically becomes x by v cos theta, and if you put this into the second equation, what you get is y is equal to v sine theta into x by v cos theta minus half g x square by v square cos square theta. And if you simplify this a little bit, it becomes y is equal to v cancels, and it is x tan theta minus g x square by 2v square cos square theta. So this is your equation which governs your path of the projectile as it travels, right? This is called the trajectory equation of a projectile. Now, notice that this equation is of the form y is equal to ax minus bx square. So anybody who has done a little bit of coordinate geometry and conic sections will recognize that this is a parabola. And it is an inverted parabola because the coefficient of x square is negative. Therefore, the shape of the trajectory looks like this, right? A few special points about this. We have that the trajectory of the projectile motion is a parabola. We will be able to find the vertex of the parabola here, which is the highest point of its motion. We have already found h is equal to v square sine square theta by 2g basically. That is the y coordinate of this highest point. We also have certain nice properties here. One property is that projectile motion is reversible. Projectile motion is reversible. But why? What do I mean by reversible? In the sense that if the direction of motion of or velocity basically of a certain at a certain point is reversed, then the trajectory will remain unchanged. Then the trajectory will remain unchanged. So how can we say that? Why are we able to say that? So think about what it means first of all. So if the particle is going like this is the projectile's trajectory. So it was going like this here, right? And it is going like this here. Suppose this v velocity you reversed and made it like this, right? What this property is saying is that the particle will trace back the same path and come back to the initial point. It will not follow some other parabola. It will trace back the same path. How can we say that this is true? We can say it by a simple proof. We can say that if you launch a particle with v, right, it is at an angle theta, right? When you reverse the direction of its velocity, what you mean to say is your velocity has become suddenly this, right? This is your new velocity v dash, right? So new velocity v dash can be defined to have what angle with the x-axis? It is this particular angle with the x-axis, right? This angle with the x-axis is basically the angle pi plus theta, right? Because pi is coming till here, 180 till here, and then theta extra here, right? So at any point, if you reverse the direction of its velocity, you are basically saying that suppose here the angle with the x-axis was theta, you have suddenly made it like this. So you have replaced theta with pi plus theta, right? Theta with pi plus theta, right? So let's look at the trajectory equation, x tan theta minus gx square by 2v square cos square theta, right? In this equation, if I replace theta with pi plus theta, let's see what the trajectory equation becomes. So if I do that, y is equal to x tan pi plus theta. Now you know that tan is going to be positive in the third quadrant, right? Tan is positive in the third quadrant. So tan pi plus theta remains the same as tan theta. And you notice that cos pi plus theta will become negative cos theta, but square will become still positive, right? So you realize that replacing theta with pi plus theta does not change the equation of the trajectory. And that's why you can say that projectile motion is always reversible. So suddenly if a body's velocity is reversed, then it means that the particle will retrace the path back to the same point, right? Also, we can say several things here actually. What you can say also is that each point, the horizontal velocity remains fixed, right? So if you are going like this in a projectile motion, initially you started off with some velocity here, and this was your angle of projection. So what was your horizontal velocity at this moment? It was v cos theta. And if someone says right now I am making an angle alpha with, this is the new velocity v dash at a particular moment in the path, and right now you are making alpha angle with the horizontal, then what is your current horizontal speed? It is v dash cos alpha, right? So this gives us a nice connection between v dash and alpha and theta. We can say that this horizontal velocity must be same as this horizontal velocity, right? So v dash cos alpha will be equal to v cos theta, right? So you'll get v dash is equal to v cos theta by cos alpha, which is sec alpha. So here there is a connection between the velocity of a particle at a certain moment and the angle that it makes with the horizontal direction at that moment. in terms of the initial values of horizontal velocity, right? So at any given moment of time, v dash velocity will be equal to vx initial multiplied by the sec alpha, where alpha is the angle that this v dash makes with the horizontal at that moment. There are several other nice properties of projectile motion, but what I will do is I will leave all of those and a lot of problems for discussion for the next session. So part 2 of kinematics basically will cover a lot of tricky problems, and we will explore different cases of kinematics and try to build up our understanding to a more advanced level. So this was basically a theory lecture. The next video will be much longer and it will be a problem discussion on kinematics. So see you next time. I hope you learned something from this video.